Let's look at how to prove the tail sum of our expectation. The question is straightforward. Demonstrate that the following statement is always true for discrete random variable x, which x actually is a non-negative or a positive integer. But we don't know what is the exact probability assigned, and we want to prove these particular equalities. Actually, whenever that we want to prove an equality, we can always think that whether we want to start from the left-hand side or start from the right-hand side. Since that we have already learned that the expectation of x is equal to the sum of x times px. So it may be easier for us to start to manipulate from the left-hand side by applying what we have already learned and to see whether we can reach to the right-hand side of the equality. So let's see how to do it. So usually, as what I recommended, starting from left-hand side, let's write down what we want to prove on the left-hand side is the expectation of x, and then we can just directly use the definition of the expectation to write down what is the expectation of x. It's nothing but sum from x equals to 1 to infinity. For each of them, x times the probability of x. So that's just the definition of expectation. And as what I always recommended, it is always recommended to write down what we want to achieve, the end goal that we want to achieve, the right-hand side of the equalities, which is the sum of k from 1 to infinity, the probability of x greater or equal to k. And I think for most of you, when you look at this summation symbol, it may not give some intuition or some relevant information. It may be helpful for you to expand it, so later you can see what is the relation to the left-hand side. So this is nothing but the probability of x greater or equal to 1 plus the x greater or equal to 2 plus x greater or equal to 3 until infinity. Okay, then next we can just let's go back to the left-hand side. We just do the same thing, expand this summation symbol. When x equal to 1, the expression will be 1 times p1. X equal to 2, it will be 2 times p2, and so on. So let's explain that. So it will be 1 times p1 when x equal to 1, 2 times p2 when x equal to 2, 3 times p3 when x equal to 3. So now we just observe a little bit. We can easily expand this into different terms. Because for the first one, we only have one copy of p1, hence we only have one p1. The second term, we have two copies of p2, hence we can split into 2. And for the third term, we have 3 copies of p3, hence we can split into 3. And then we sum them together, is the same. The reason we want to do that is that if we looking at the right-hand side, the probability of px greater or equal to 1 is nothing but p1 plus p2 plus p3 plus until infinity. So this is the probability of x greater or equal to 1. Then for the probability of x greater or equal to 2, you can just write as p2 sum p3 until infinity. And similarly, for probability of px greater or equal to 3 is nothing but the probability of 3, some probability of 4 until infinity. So you see this actually is exactly the same as this. Hence, the left-hand side of the equation actually is equal to the right-hand side of the equation. Then the proof actually is already done. So for this tail of sum, actually is another way for you to calculate the expectation of a discrete random variable when the value of the random variable is positive.